Okay, what we're being asked to do is just confirm the conclusion of Stokes' theorem, which says that this side equals this side. So what we're going to do is set up stuff and then work out the left-hand side. In the second video, we're going to work out the right-hand side, and we'll see that we get the same answer. That's all that we're trying to do here, is get familiar with the settings. Meanwhile, what's the setting? They give us a surface. We can see that that's a hemisphere. It's the top half of a sphere of radius 2. We're being oriented up like this. So there's the surface. The boundary is C. It's actually this edge down here. Let's actually put the C over here. Just more comfortable with it there, I guess. We're supposed to find the orientation of C by standing on the surface and then walking along the edge so the surface is to our left. A different way of saying this exact same thing is go in the direction of positive and look down on the surface. And if you're doing things right, when you look down on the surface, you should see counterclockwise motion. So this is really what we want, right? We want to find parametric equations for C, which is in the XY plane, so that the movement is going to be counterclockwise. So I'm going to erase the surface for now because I'm going to start focusing on the left-hand side. And I want parametric equations for C. I do need to know exactly what circle that is. Remember, that circle is the intersection of the hemisphere, which is z equals 4 minus x squared minus y squared, with the xy plane, which has the equation z equals 0. I square both sides. I get 4 minus x squared minus y squared equals 0. I get 4 equals x squared plus y squared. And we know how to find parametric equations for this, right? We start writing down, let's see here, I want x equals 2 cosine t because the radius is 2. And we have y equals 2 sine t, which is great. One thing I'm going to need, by the way, because this curve actually lives in 3 space, it just happens to live in the xy plane, we also need to include z equals 0. We're going to need that, for example, because we have a 3-dimensional vector field. So there's our parametric equations. X equals 2 cosine t, y equals 2 sine t, z equals 0, and we're going to start focusing on the line integral, which is the left-hand side, what we want to calculate. So I'm going to leave the vector field there for the moment. I know I'm supposed to just start doing this the way we normally just calculate line integrals. So this is going to be C, this is going to be f dot dr. Now remember how we do this from scratch is we put a dt down here like this, a dt up here like this, and we need to rewrite our parametric equations so they're in the form r of t. So I'm going to write down r of t, and we know what this is from down there. This is going to be 2 cosine t I plus 2 sine t j plus 0k. I can get rid of this now. And we want dr dt, not just r. So to get dr dt, we just take the derivative. I get dr dt like this. This is going to be minus 2 sine t I plus 2 cosine t j plus 0k. And we're going to start writing down the line integral. F looks like 2x minus y, and then y squared, and then y squared z. And I'm supposed to dot that with dr dt, so this is minus 2 sine t like this, and then 2 cosine t like this, and then 0 like this. And I know there's a dt over here. We still need limits of integration, and I need to put everything in terms of t. Now remember, the only place we're actually interested in this case is a force field, are actual arrows that live on the curve. Well, for on the curve, x equals 2 cosine t, y equals 2 sine t, and z equals 0. So we're now going to just start filling in all the details. I now know, since I'm just going once around a circle, I'm going to go from 0 to 2 pi. I'm going to start filling in stuff. 2x is going to be 4 cosine t, like that. Minus y is going to be minus 2 sine t, like that. Y squared is going to be 4 sine squared, like that. y squared z is going to be y squared times 0. So that's just 0. I'm not going to have to fuss about that one. And then I put minus 2 sine t here, and 2 cosine t here, and 0 like that. And we want to turn that into an integral that looks like a Calc 1 type integral. So we're going to work our way back up now. I still have 0 to 2 pi. Let's see here, I'm going to have minus 8 cosine t sine t. Minus 8 cosine t sine t, like that, plus 4 sine squared. T like that, plus 8 sine squared t dt, like that. Now I'm going to break this up into 3 little integrals. The first one, let's see here, I'm going to do this by guess and check. What I think I'm going to see is 4 cosine squared. Because the derivative of cosine is minus sine. And I'm going to try that. I think that's actually right. And I want to go from 0 to 2 pi there. And then we get the integral in the middle. That's actually the only one that's actually going to be hard. This is going to be 4 sine squared dt. And then, yeah, this is, when I dotted these two things together, I was supposed to get 8 sine squared cosine squared. No, 8 sine squared cosine. What do you think? Is that right? 8 sines, yes, that's right. Now that one's now easy too. I think that one's just 4 sine. Ooh, nope. What do I want? How about 8/3 sine cubed? What do you think of that? The 3 comes down, the 8 is sitting there, then I multiply by the derivative. Yeah, that also works. Yeah. Now cosine's periodic of period 2 pi, so this part here is just 0. That didn't give me anything. Sine is also periodic with period 2 pi, so when I plug in 0, I get the exact same answer I get when I get 2 pi, so I get 0. So if there's any work done at all, that's where it's all going to come from. Now, we actually did this integral several weeks ago. There are 3 different ways of doing this, or 4. I guess what I'm going to do is use an identity. We should see each way several times if we can help it. I know that sine squared t is actually equal to 1 minus cosine 2t over 2, like that. That's going to say that 4 sine squared is going to be that times 4. So what I'm going to get here is going to be 2 minus 2 cosine t. And that's not doing an antiderivative yet. Doing just this piece. This is 0 to 2 pi. So I'm going to get 2 minus 2 cosine t, 2t, sorry, like that. I take the antiderivative now. I'm going to get 2t. And I think minus sine 2t from 0 to 2 pi, like that. When I plug in sine of 4 pi, I get the same answer as when I plug in sine of 0. So the only thing I'm going to get that's not 0 is going to be what I get when I plug 2 pi into 2t, and I get 4 pi. And I think that's the answer. We will check by doing the other side in the next video.